So your checkup for today had you, first of all, determining whether the angle between two vectors in 4 space is acute, right, or obtuse. And then also determining both the rank of this matrix, which is 2 by 3, and then also determining the rank of its transpose, or predicting, rather, the rank of its transpose, ideally without doing any additional computation. So starting on the left, how did you determine whether or not these two vectors make an acute angle, a right angle, or an obtuse angle?
And the dot product over 2.
Right, so dot product is the beginning of our whole story of orthogonality. So how does a dot product work? How'd you do it?
It's component by component. You
Okay.
multiply them together and then add with the next.
Okay, so you multiply the components by one another. Negative 1 times 4, 0 times 1, 3 times 2, 2 times negative 1. And then you take those results and you add them together. And so you did that. And you found that that dot product was 0. Negative 4 plus 0 plus 6 minus 2. Yeah, okay. So the dot product ended up being 0, so what did you conclude? Yeah. So having a dot product of 0 in vector calculus is how you identify a right angle, regardless of which Euclidean space you happen to be working in, right? 2 dimensions it works, 3 dimensions it works, 4 dimensions it works, even if we can't write, sketch a diagram that's convincing. And so that's really, this is the beginning of our orthogonality story. After all, orthogonal is just another word for right angle. So I could have put the word orthogonal here, but I decided to go easy on you. It is a word that we need to add to our vocabulary beginning today. But then the second link, if you watch the videos, is that this takes on a linear algebra realization when we think of the dot product of two vectors. How? What is this going to have to do with linear algebra and matrices? What is v dot w the same as? Right. So thinking of w, for example, as the column vector, and this is how we think of vectors in linear algebra, right? We think of points in R2 as being 2 by 1, 2 rows, 1 column, column vector. So we'll think of w as a point in R4. We can think of it like a column matrix. And then if I want to multiply its components by the components of v in exactly the same way that we did here, then what I need to do to v is I need to turn it on its side. And that's where our transpose comes in. If I turn v on its side into negative 1, 0, 3, 2, then when I do this matrix multiplication, because matrix multiplication goes across the row and down the column, I end up getting exactly the same thing as we computed over there. And so the definition of two vectors being orthogonal, v is orthogonal to w, if what? Yeah. If v transpose w equals 0. Where here v and w are thought of as column vectors, right? So v transpose is then a row vector, and the product of row vector by column vector is exactly what we mean by dot product. So that's the notion that gets us started into the process of using transposes to talk about orthogonality. And so because the question of projecting a point onto a subspace has so much to do with perpendicularity, as we decided on the first day of the class, it's perhaps not so surprising that the transpose is going to be a part of the conversation. The well of linear algebra is a very deep one, and we have to go back to it in number 2 and get a drink. How do we find the rank of this 2 by 3 matrix?
Reduce or echelon form.
Okay, so the first thing we need to do is some reduction. And luckily, this reduction takes only one step. Second row added to twice the first row. That should be enough to give us not the reduced row echelon form, but as Greg was saying, it gives us a form in which we can identify what are we really looking for here? What do we need to know in order to determine the rank of a matrix? Yeah.
If we have like placeholders
Okay.
in the, I don't know, like the diagonal spot there, like where the ones are supposed to be.
Okay.
Yeah.
So looking on the what would be the diagonal if it were a square matrix, then what are we looking for here? So here's a number, and here's a number, both of which are pretty important for us. What do we call those numbers in linear algebra? pivots. What makes a pivot, by the way? How do you know one when you see one? Zeros to its left as well as,
Zeros below.
yeah, so zeros have to be only zeros below and to the left. So this -1 is a pivot because there's only a 0 underneath it, and, well, there's nothing to its left, and so that's okay. Same thing with this 8. This 8 is a pivot because there's nothing underneath it, which is okay, and there's only zeros to the left of it. So we find that this matrix has 2 pivots in it, and so what do you conclude?
The rank is 2.
Rank is 2. Okay, so now is a good time to remember what rank actually means. We'll figure that out in just... For me, in linear algebra, my aha moment, and you probably will recognize this the more of my videos that you watch, because I keep coming back to this same diagram to think about what a matrix is doing by thinking of it as a linear transformation from one vector space into another vector space. This is a 2×3 matrix, and so it describes a linear transformation from R3 into R2. Oops. Because it's capable of multiplying a vector that has 3 components and producing from that product a vector that has 2 components. So that's why this works the way that it does. And what does the rank of A tell us about this linear transformation? What's it quantifying? Or what's it measuring? Let me flesh out this picture a little more. One of the ways we can flesh this picture out is by thinking about what we would get by taking some simple vectors back in my domain, which is R3. And when I say simple, I mean I'm just going to take the standard basis vectors. 1, 0, 0, 0, 1, 0, and 0, 0, 1. And I'm just going to multiply A by those simple vectors. What makes that a particularly simple thing to do is that, for example, when I multiply A by 1, 0, 0, so imagine putting 1, 0, 0 there, what I get out of that matrix product is exactly just the first column of A. So 1, 0, 0 under this function has an image, which is the first column of A, -1, 2. So I'm just going to fill that in over here. 1, 0, 0 turns into the vector -1, 2. So matching colors to colors here, the green vector on the left maps to the green vector on the right. 0, 1, 0, the second standard basis vector, maps to the second column of A. So it maps to 2, 4, which is up here somewhere. 2, 4. And then the third standard basis vector, 0, 0, 1, is going to map to the third column, which is 0, 1. So something like this. So that's the images of all 3 of these vectors under the linear transformation, which is defined by multiplication by the matrix A. So what does 2 have to do with it? What is the 2 measuring here? One of the things we can say right away is that, well, let me ask this. What is the largest that the rank of this matrix could have been? What's the biggest rank that a 2×3 matrix can have? 2. Why?
We have 2 rows.
Right, we're limited by the number of rows because every row may only have at most 1 pivot. Every column may only have at most 1 pivot. So there's no way our rank is going to be any bigger than 2. Okay, well, on this diagram, there is a vector space whose dimension is 2, which will limit the dimension of any vector subspace within it to being at most 2. What space is it? It's the codomain, it's the R2 that's over here on the right. So if our rank is limited by that number, it means that our rank is hopefully measuring the dimension of some subspace, this R2. What subspace is it? Or what's it called?
The XY plane.
Well, it happens in this example to be the XY plane. But in general, it's the column space of A. So here's the connection. Here's what a pivot position is actually telling us. If I take these 3 vectors over here. These three vectors are the columns of A, right? Negative 1, 2, 2, 4, and 0, 1. And I take their span. I say the set of all of their linear combinations. How do I know what dimension that span is? If I have these three vectors, why is it kind of obvious that if I take these three vectors and take their span, that I'm going to get something which is only two-dimensional? Well, they all live within two dimensions, but not every, right. So if I had, for example, negative 1, 2, and negative 2, 4, those two vectors live within R2, but their span would only be one-dimensional. So why is the span of this set of three vectors only two-dimensional? The rank is 2. And every pivot column, this again reaches back to linear algebra. What do pivot columns mark? They mark those columns which are linearly independent. If you'd like some linear algebra review and you want to look back at your old notes, probably the section which is going to have the most bang for your buck is going to be the section on linear independence, basis, and dimension. Right? There's usually one section in every linear algebra textbook that covers those things, and that's really where the rubber meets the road in linear algebra. So every column with a pivot is independent of every other column with a pivot. Those columns without pivots are redundant. We can write them as linear combinations of the others. So since we had two pivots, we have two linearly independent columns, and we would get the very same span if we forgot about that third column altogether. Right? The green and purple vectors by themselves give us the same span as the green, purple, and blue altogether. So that's the rank of A. The pivots mark the independent columns, and therefore they mark the dimension of the column space of A. So rank is the dimension of the column space of A. How many linearly independent columns do we have? That's the rank. So if that's the case, what do you think about the rank of A transpose? What did you say, first of all? 2. Did everyone say 2? 2. Okay, I agree with you, but why? You might have computed it directly, but I tried to dissuade you from doing that. Because why is it reasonable to expect that A transpose will have a rank of 2? Mark?
If you have 3 rows, 2 columns, you can't have more than 2 pivot points.
Well, we certainly can't have more than 2, right? If we turn this matrix on its side, we know we're not going to get any more than 2 pivots. It's not possible because we're going to be limited now by the number of columns being 2 and the number of rows being 3. So that explains why it's no more than 2. Why is it exactly 2?
Even if you flip A on its side,
Mm-hmm.
when you go from 3 dimensions, you'll still go into a 2-dimensional.
Well, not exactly. So this gets to the point of how a transpose works. Because the transpose of A is going to be a 3 by 2, 3 rows, 2 columns matrix. The transpose of A goes the opposite direction as A does. It operates on 2-dimensional vectors and produces 3-dimensional vectors. And so the rank of A transpose is going to be the dimension of some subspace of R3. But that subspace is 2-dimensional comes from the fact that A transpose somehow is going to only have 2 linearly independent columns. But it only has 2 columns altogether to begin with. So it's saying both of the columns of A are linearly independent. Why are the columns of A linearly independent? Because the rows of A are linearly independent. Sorry, why are the columns of A transpose linearly independent? Because the rows of A are linearly independent. And that's the beautiful thing about pivots, is pivots don't care about columns versus rows. That a pivot, the job of a pivot is not only to mark which columns are linearly independent, but they also mark which rows are linearly independent. And so rows that have pivots are independent from one another. Rows that have columns, or pivots are columns that have pivots are independent from one another. And therefore, we're going to always have as many independent rows as we have independent columns. And for that reason, every matrix has the same rank as its transpose. This is a fact that if we do things right over the next class and a half, will be crucial to our understanding of why we can solve the normal equations when we want to solve them.